Hello everyone. In this video, I will introduce AULID, a fully on-disk updatable learned index. Learned indexes have shown strong performance in memory, but most real database systems still rely heavily on-disk indexing. This raises the key question behind our work. Can we build an on-disk learned index that consistently beats the B+ tree? However, as shown in the figure, applying existing learned indexes on disk cannot beat B+ tree. This table shows the NOM blocks nodes fetched in read-only workload on the FB dataset. L refers to lookup and S refers to scan. We can see the first challenge that compared to B+ tree, a learned index cannot guarantee to reduce I/O costs when searching data on disk, especially on the scan query. This figure shows the latency breakdown in insert-only workload on the FB dataset. We can see the second challenge. Compared to the B+ tree, most learned indexes suffer from large insertion overheads. Different indexes may have different bottlenecks. To address these two challenges, AULID is designed around 5 principles. The first is to reduce tree height, as each extra level usually means another disk access. The second is to support model-based search and insert where it is truly helpful. The third is to make structure modification operations lightweight, since updates are a major problem on disk. The fourth is to support duplicate keys efficiently, essential in real systems. And the fifth is to provide better scan performance. The first key design is the leaf node layout. AULID uses B+ tree-styled leaf nodes instead of learned leaf nodes. This is important because leaf nodes are the most frequently modified part of the index. If we use a learned structure there, maintaining models would introduce a large amount of extra I/O during updates. By keeping the leaf nodes B+ tree-styled, AULID achieves 3 benefits at once. It makes updates lighter, which supports lightweight SMOs. It supports duplicate keys naturally, just like a standard B+ tree. And it enables efficient scans because sibling links and packed storage make it easy to move to the next item. The second key design is the inner node layout, where AULID actually uses the learned index idea. AULID uses FMCD-based mixed nodes with linear models to reduce the tree height and guide search efficiently. A critical detail is that the model is stored in the parent, so each level still needs only one block read. That is very important for disk efficiency. To handle harder regions of the key space, AULID also introduces 2 additional node types, packed arrays and 2-layer B+ tree nodes. Packed arrays absorb small numbers of new key block pairs without creating new mixed nodes, while 2-layer B+ tree nodes bound the tree height when conflicts become larger. Next is the design of structure modification operations. Since the inner nodes only index the maximum key of each leaf, they are updated less frequently. And because packed arrays and 2-layer B+ trees can absorb many insertions, AULID avoids triggering new mixed nodes too often. At the same time, AULID monitors the tree height of each branch. If a region becomes too deep after many insertions, it reconstructs the structure adaptively to keep the height bounded. This is a crucial part of the design. Without controlling height growth, an on-disk learned index can eventually become worse than a B+ tree after many updates. AULID also includes specific read and scan optimizations. The first is scan forward. When a lookup lands at the predecessor leaf, AULID scans within the current block to find the next valid data slot, which often avoids an extra block fetch. The second is fulfill. During bulk loading, AULID fills preceding null slots with the address of the next data slot. This helps eliminate irrelevant block scans in read-only workloads. Finally, let us look at the results. AULID achieves the best throughput across all tested datasets and workloads, with up to 2 times higher throughput than the best baseline. At the same time, AULID keeps storage usage and build time similar to a B+ tree, which is very important for practical deployment.